Okay. All right. Hello, everybody. It's a great pleasure for me to be here. I'd like to thank the organizers for inviting me. Actually, I remember I've used these volumes from the British Combinatorial Conference all through my career, the many interesting survey articles I took from there. So it's a great pleasure for me to actually speak here. But I think we should also all thank the organizers for organizing this conference this year with a round of applause. So this is the last talk, and I think it's a good place to do this. All right, so I want to speak about the graph isomorphism problem, and these are my main collaborators on the work. I'll be mainly speaking about Daniel Neuen and Daniel Wiebking, our former PhD students who recently graduated, and Pascal Schweitzer is now a professor at TU Darmstadt, but was at Aachen for a while as an assistant professor when we did this work. So the graph isomorphism problem. It's a simple, well-known problem. Given two graphs, decide if they are isomorphic. So for example, if you look at these four graphs, you may see that they are indeed all isomorphic. You may also see that it's not always so easy to detect this, in particular with this more random drawing of the graph that I have here. It's not so easy to match it to the other ones. And these are just 8 vertex graphs. So in general, it's a difficult problem. It's also a very interesting problem. It has interesting mathematical structure, and that's, I guess, what makes its complexity unusual. And to highlight this, let me just point out that the problem of computing the automorphisms of a graph. The automorphisms form a group, and computing a generating set for this group is actually equivalent to the decision problem, the isomorphism problem. And this group structure is really what helps us to design algorithms and what makes the problem quite interesting, I think. So the question is there a polynomial time algorithm for solving the graph isomorphism problem, or equivalently computing generators of the automorphism group? It's a long-standing open problem. I'll say a little bit about the history in a minute. What we know, and that was a big breakthrough in 2016, is that graph isomorphism can be solved in quasi-polynomial time. So that's time n to some polynomial in the logarithm of n, somewhat close to polynomial. And before that, for, I think, since 1983, the best known bound was, let me write this down, 2 to the big O of square root of n times log n. Okay, that was due to Babai and Lux. So compared to that, Babai's quasi-polynomial bound is indeed a huge breakthrough. And I will say a little bit about this result and how it's proved, and I will speak about subsequent work. So now I can't, okay, let's briefly look at the complexity theoretic situation for the graph isomorphism problem. So you know we have the polynomial time solvable problems, we have the class NP. A graph isomorphism is obviously in NP because we can easily verify that a mapping is an isomorphism if we know the mapping. But it's not known whether graph isomorphism is in polynomial time or whether it's maybe NP complete. And actually, it's one of the very few natural problems with this property. There are actually good reasons to believe it's not NP complete. One is the quasi-polynomial time algorithm I mentioned on the previous slide, but even before that, we had results saying that if graph isomorphism is NP complete, then the polynomial hierarchy collapses to its second level, which is regarded as unlikely. So there are good reasons to believe it's not NP complete. I don't know of any good reasons to believe it's not in polynomial time. Actually, I believe it's in polynomial time. So what do we know in terms of lower bounds? Well, if we look inside of polynomial time, there's the class of all problems solvable in logarithmic space, and then by a non-deterministic logarithmic space algorithm. And we know that graph isomorphism is hard for this class NL, actually even a slightly larger class, the equivalence class of solving or computing the determinant of a matrix. Okay, so that's the best known lower bound we have, but for example, we do not know if it's p time complete, as hard as any other problem in polynomial time. Okay, and as I said before, we know it's in quasi-polynomial time, although this is not fully compatible with the picture. It's, for example, not contained in NP for all we know. All right, so that's what we know. Let me start now with a brief history of the problem that goes back a long time and was first studied actually in chemistry, or in the context of chemical information systems. So we can represent chemical molecules by these diagrams, which are essentially graphs, as you know. And now imagine you have a database where you have a huge list of such molecules, and you find a new one and you want to know if it's already in your database or not. Then essentially you have to solve the isomorphism system. So one of the first publications I know that is about graph isomorphism testing as an algorithmic problem is this one here, which is indeed about finding chemical records, as you see. Okay, then in the computer science literature, the problem appeared in the 1960s. So these two papers from 1964 are the earliest ones I know. But it really gained prominence in the 1970s. People defined the class NP and the concept of NP completeness. And in a very influential paper, Karp showed that many natural search and optimization problems are NP complete. He also mentions graph isomorphism in his paper, but as an open problem. Okay. And later it was also named an open problem in Gary and Johnson's influential monograph on NP completeness. So by the end of the 1970s, people started to speak about the graph isomorphism disease because, well, they couldn't put it in this picture of NP complete problem, polynomial time solvable problems. And in a sense, this is where its prominence comes from. And this hasn't changed so much since the 1970s. We still don't know the exact complexity, although we know a lot more algorithmically. And this is largely due to a group theoretic approach to the problem, which was first proposed by Babai in an unpublished technical report from 1979. He came up with randomized algorithms for a certain special case of graph isomorphism. I don't want to get into it. A year later, first Hopcroft and Lux de-randomized it, but the real breakthrough was a paper by Lux. I think the conference version appeared in 1980, and the journal version 1982, where he used some non-trivial group theory to show that isomorphism of graphs of bounded balance or bounded degree can be solved in polynomial time. And I'll say a little bit about that algorithm later. It's really the basis for most of the stuff that happened afterwards. Okay, so this was an extremely important paper. And then, of course, there was Babai's breakthrough. Actually, he announced his result in late 2015. And as you can see from this screenshot, that the means of communication have changed in the meantime, although he's still using a blackboard, which is somewhat consoling. So that's this. Now, so much for the history of graph isomorphism as a theoretical problem. It has also been studied in practice, and it has quite a few practical applications. And basically, from a practical perspective, it's not a very hard problem. By now, there are very good tools that can solve graph isomorphism quite well on relatively large graphs, and they go back to this tool Naughty by Brendan McKay, and he introduced it in 1981, so around the same time as Lux did his work, and it's based on individualization refinement, essentially a combinatorial algorithm, also uses a little bit of group theoretic ideas to prune search trees there. And this was already very good in its initial version, but this has been further developed. So now it's combined with Piperno's traces tool, and that's really still the state of the art. And it's really difficult to find instances these tools cannot solve. So that's also quite different from NP-complete problem. For NP-complete problems like SAT, well, many instances that appear in practice can be solved well. It's used in industrial verification on very large instances, but it's still not very hard to find hard instances for satisfiability solving. For graph isomorphism, it's not easy to find instances that these tools cannot solve. And let me say a few words about applications of graph isomorphism. There's basically two types of applications. The first one, which I call graph matching here, is pretty much what you would think of. You want to match two graphs to see if they are the same. For example, the chemistry example is the prime example of this. You want to match graphical representations of molecules. In computer vision, this has been used a lot. For example, face recognition, faces are represented by graphs and they want to match them. Or in static program analysis, in program verification, we want to match code fragments represented by graphs, for example, to detect malware hidden in programs. Okay, and then the second type of application may not be the first you think of, but it may be the more important one, and that is to exploit symmetries to solve hard problems by reducing the instance sizes or simplifying the instances, or pruning search trees in backtracking algorithms. So this has applications, for example, in SAT solving, integer linear programming, and so on. Now, it turns out that often for these applications, in particular of the first type, the matching type, but also the symmetry reduction type, it's actually enough to solve graph isomorphism approximately, so find approximate matchings between graphs rather than exact isomorphisms, which leads to what I call the graph similarity problem. And that's also a very interesting problem, actually one where I've been working on in recent years. This is not what this talk is about, but I just wanted to point out that it's also quite interesting. Complexity, theoretically, it's the harder problem because you lose the group structure. But now we want to talk about graph isomorphism. And even though I said the important progress has been made through these group theoretic algorithms, let me start by talking about combinatorial algorithms, actually just one type of combinatorial algorithm that dominates most others, the so-called Weisweiler-Lehmann algorithm. So let me show you this one. So first in the one-dimensional version. So it's 1WL, one-dimensional Weisweiler-Lehmann algorithm. It's also known as color refinement or naive vertex classification. And actually, this is an algorithm that has been rediscovered many times in different areas. The earliest reference I'm aware of is a 1964 paper, which also appeared in the context of chemistry. And the algorithm goes as follows. Initially, all vertices of a graph get the same color. So the algorithm just colors the vertices of a graph. And the intention is to detect differences between vertices, structural differences. Okay, initially we don't know anything. All vertices have the same color. Okay, and then two nodes get different colors if there's some other color or the same, the one they have, such that they have a different number of neighbors of that color. Okay, so the coloring refines, and we repeat this process until the partition into color classes stays stable, and then we call the coloring stable. All right, so let's look at an example. So here we have a simple graph. Actually, I believe it's a tree drawn in a somewhat odd way, but it doesn't matter. So initially, all vertices have the same color, some dark blue. And now let's see what happens. So for example, this one here has one neighbor, this one has three neighbors, this one as well. So these two should keep the same colors. This one gets a different color. Okay, that has two neighbors, should also get a different color. And that's pretty much what happens. So the coloring is now by degrees of the vertices. Now let's see, we look at these two. Now that one has a purple neighbor. That one does not. So in the next round, they should get different colors. And indeed, this happens here. Okay, and I think we can do one more color and get something new. Do we? Yes, because, well, whatever. I think you understand how it works. And it turns out this is the stable coloring that we get after round 3. So if we continue, the color classes don't change. So it's an extremely simple algorithm. It's also very efficient. If you implement it in a clever way, it runs in time almost linear. So n is the number of vertices, m the number of edges times the log factor. We wondered a while ago if we can get rid of the log factor. It seems we can't, at least for a very large natural class of algorithms. We proved a lower bound of n log n. So it's not actually linear, but still this is very efficient, and there are no large hidden constants. So that's really a great plus. And this algorithm has many applications. It's part of basically all modern graph isomorphism tools, but also has applications, for example, in machine learning and combinatorial optimization. And part of the reason is that it's so efficient. In particular, in machine learning, there are graph kernels based on this. And the real plus is that the algorithm is so efficient. So this is good. How it's now actually, I'll tell you on the next slide how it's used in practical graph isomorphism tools. Here I just want to discuss how it's used in general in graph isomorphism testing. So the idea is to detect non-symmetries, right? We give different colors to vertices where we have found some difference, and we clearly do this in an isomorphism invariant way. So if two vertices get different colors, they belong to different orbits of the automorphism group. Okay. Unfortunately, the other direction does not hold. Okay. So for example, this is a very simple graph where we have two orbits of the automorphism group, the triangle and the cycle of length 4, but color refinement does nothing because, well, initially all vertices are black. Every vertex has two black neighbors, so nothing happens, and the algorithm is already stable before it even starts. Okay, it fails on very simple graphs. On the other hand, on random graphs, it works perfectly. Okay, usually after 2 rounds, this can be shown, it stabilizes with high probability. Okay. If we want to use it as an isomorphism test, we would run it on 2 graphs in parallel and then compare the color histograms. That is, if some color appears more often in one graph than in the other, we would say, and we would know they are non-isomorphic. It could be that they end up with the same color pattern, are still not isomorphic. So for example, a cycle of length 7 and this graph here would have the same color pattern, 7 black vertices, but they are not isomorphic. Okay. So in some sense, since it cannot distinguish such simple graphs, it's not a very powerful isomorphism test, but it can be used as a subroutine of more powerful isomorphism tests. And that's what is done in practice. So basically what we do is we run color refinement. Let me show you. We have a graph here. We run color refinement. These are the color classes, 2 classes for this example graph here, red and blue. And now, if our goal is to have individual colors for every vertex. So every vertex should have a different color. And then if we assign the colors in a canonical way, we can easily see if the graphs are isomorphic. Okay, so what we do is we artificially say, okay, let's pick one of the red vertices and give it a different color. So in this branch, we pick that vertex, in this branch, we pick that vertex, and so on. And then we go on. Now, this vertex has a new color. When we run color refinement, the coloring changes. So the neighbor of this individualized vertex will have a different color as well. So it looks like this. Well, still 2 red vertices. So we recolor one of them, run color refinement again. And then all vertices have different colors, and we can easily detect isomorphism. We built this tree, and then we can see, basically we have a canonical representation of the graph. We can derive it from this, or we can also build the tree for 2 graphs in parallel, but that would be less efficient, but also work. Okay, and then there's various very clever techniques to prune this search tree to avoid going to the essentially very similar branches. But I don't want to get into this. But this is how graph isomorphism is solved in practice. In theory, this Weisweiler-Lehmann algorithm has also been strengthened to higher dimensional versions. And the k-dimensional version works in essentially the same way, iteratively refines the coloring, but now it's a coloring of k-tuples of vertices rather than just vertices. Now that costs us a lot in terms of running time. It's now n to the k plus 1. But it also makes it much more powerful. So here, for example, you see the color classes of pairs of vertices where the underlying graph is a cycle of length 8, I believe. Okay. And the interesting thing about this algorithm is that it subsumes many other combinatorial, algebraic, mathematical programming algorithms for graph isomorphism. And there have been a lot of results, many of them only in the recent years showing this. So Weisweiler-Lehmann is really extremely powerful. And usually when I talk about graph isomorphism, somebody comes up after the talk and says, why don't you do this? What do I know? Count the triangles, and then the triangles where one vertex has 5 neighbors and the other 7, and then it distinguishes all graphs I know. And usually everything people come up with is subsumed by the 3-dimensional Weisweiler-Lehmann algorithm. You can bet on it. Okay, except for the group theoretic stuff, but that's usually not something you cook up during a talk. So then that's what we have here. We also have results showing how powerful it is. So for example, this one, for every graph class with an excluded minor, say the class of planar graphs, we can find a k, a constant k, such that the k-dimensional Weisweiler-Lehmann algorithm is a complete isomorphism test for the graphs in this class. Okay, so for planar graphs, we know this k is 3. For bounded genus classes, we have shown it's linear in G, I think 4G plus 3 or maybe 3G plus 4, I forgot. For tree width, we know an upper bound of k, but that's about it. It's quite interesting to try to get good bounds on these k's. We call this the smallest such k for a class the Weisweiler-Lehmann dimension of this class. That's an active research area, but again, not what I want to talk about today. On the other hand, we know that there are non-isomorphic graphs, and actually not very large graphs, so graphs of size linear in K that are not distinguished by the K-dimensional Weisweiler-Lehmann algorithm. And that's a seminal result by Sai, Führer, and Immermann from 1992. Okay, so we have this Weisweiler-Lehmann algorithm. It subsumes most other combinatorial approaches, but the group theory stuff brings something new. So let's look at this. Okay, so what we know is that the solution space to the automorphism problem is a group. So it has a very nice structure. And this is something we can try to explore in our, exploit in our algorithms. Okay, and a framework for this has been cooked up by Lux in this paper from 1982 I talked about. It's basically a divide and conquer strategy for solving the problem. Okay. And before I explain the method, only very roughly, but I'll say a little bit about it. Let me show you the main results that were obtained by this methods and refinements of this method. So the first two, and these are really the most important results, is Lux's original result. So graph isomorphism on graphs of maximum degree D can be solved in time n to the big O of D. And this was improved a little bit later to D over log D. And then Babai, for his quasi-polynomial time algorithm, also used this method, although he introduced many, many new ideas to make it more powerful. But still, the basic skeleton is still there. Okay, and now some recent results that we have obtained. And these are still quasi-polynomial algorithms, but instead of putting the size of the graph in the exponent here, we can put just some parameter of the problem. So for example, we can put maximum degree, and that was our first result. So we have an n to the polylog of D algorithm. So that basically improves Babai's and Lux's results simultaneously. If you look at Babai's proof for graphs of logarithmic degree, it wouldn't be any better than this. Whereas ours has a log n there if the degree is log n. Okay. And then over the years, we realized, okay, we can do this for other parameters. For example, bounded tree widths. That's what Daniel Wiepking proved. And for bounded genus, that's what Daniel Nguyen proved. And then we put everything together and showed that for graphs excluding, or for graphs of Hartwigger number H, so that's the size of the largest click minor in the graph, or 1 minus the size of the first excluded minor minus 1, we can also have n to the polylog of h. And this is the result I want to talk about for most of the rest of the talk. In the meantime, Daniel Neun has improved this further to what I would like to call the topological Hartwigger number. I don't know if there's a reasonable name for this. It's the same, except that now we look at topological subgraphs or topological minors, however you want to call it, instead of minors. Okay, so there we also have this n to the polylog t. Okay, and now let's start to get a little more technical. And one slide of background from computational group theory will be necessary. And the first fact I want to mention is a well-known and very simple fact that every group has a generating set of at most logarithmic size. And this allows us to represent the automorphism group of an n-vertex graph in by a generating set of size, well, basically big O of n log n or something like this, okay? Certainly polynomial. And we will always, when we do computations on groups, we will work with generating sets. But then, of course, if you only have a generating set for a permutation group, it's not clear what you can still say about the group. Turns out that you can actually say quite a lot. Okay, before I tell you a few examples, let me mention the second fact. Actually, I mentioned it before, except that I called the problem GA before the problem of computing a generating set for the automorphism group. Okay, and this is actually the problem we're trying to solve. Okay, given a graph, let's try to compute its automorphism group or a generating set for the automorphism group. Okay, and now, come on, a few things, a few basic routines on permutation groups that we can do if we just know a generating set. So there's a general technique called the Schreier-Sims algorithm, which allows us to compute what is called a strong generating set, which is a nicely structured generating set, and allows us to answer many basic questions. So we can always compute orbits, we can compute minimal block systems. And what is a block system? It's basically an invariant equivalence relation, and it's a minimal block system if the number of equivalence classes is minimal. Now, for these, you only need elementary algorithms. For example, for testing membership, you need this Schreier-Sims strong generating set idea. And then you can do certain other things. For example, you can, let's say you have a membership test for a subgroup. And you want to compute a generating set for this subgroup. You can do this, but only in time polynomial in the index of the subgroup. So if the subgroup has small index, you can do it in polynomial time. Otherwise, you can't. And this is actually, this computing generating sets for subgroups is something that is very important. And if we could solve this, we'd basically be done with automorphism, with isomorphism testing. Okay, so how does the divide and conquer strategy go? I'm simplifying a little bit here, but the basic idea is you do a recursion over graphs, and at the same time groups, permutation groups operating on these graphs. So the groups are always gamma here, the graphs are G. In the literature, this is sometimes used differently. So instead of computing the automorphism group of the graph, we only want to compute the part of the automorphism group that is in this group gamma. Now, that doesn't seem to make much of a difference, in particular because usually we want gamma to be a group that contains the full automorphism group. The difference is that the problem can get simpler if gamma is a simpler group. So by making, for example, gamma smaller and smaller, we can simplify the problem. So in the recursion, we will either make progress on the graph or on the group that we still have to consider. And that's the idea. Actually, we don't work with the graphs because when we split the graphs along splits induced by the groups, we do not necessarily get proper subgraphs. We also have to think of the edges that go across the cut. So we rather take an abstract representation of the graphs by something people in this area called strings. I would rather say colored sets, but whatever. But I don't want to get into this. That's good enough to explain the basic strategy. And the strategy is as follows. If the group gamma, not G, is not transitive, that is, it has more than one orbit, and remember we can find the orbits, then basically we recursively process all the orbits and put the results together. And that can be done, okay? The second case is, it's transitive, still gamma. It's transitive, but not primitive. That is, it has a non-trivial block system, a non-trivial invariant equivalence relation. Then we can compute this block system. That's something we can do, and reduce the problem to a couple of subproblems. The subgroup that fixes all the blocks setwise. Okay, and now if we look at this subgroup, this will have many orbits, because now all the groups, if the blocks are fixed, now all the blocks are orbits. So in the next step, we can recurse by being not transitive. So that's certainly progress. And then we have the action of the group on the blocks. So if the blocks are non-trivial, we act on a much smaller set. Okay, so in both cases, we make progress, and the group is always gamma, and I don't want to correct this all the time. Okay, so that's what we do. And then it may happen that the group is primitive. So neither has orbits nor a non-trivial block system. Then we're basically stuck. And in this situation, what Lux did is essentially use brute force. And that means compute the full primitive group, not just a generating system, but all elements of the group. And then you can go on. If you know the full group, things get easy. Okay? But this group can be very large. So this does not always help. Okay, and now what Bavai did is in some sense based on a group theoretic fact that up to one simple family of groups, sometimes known as Johnson groups, that are alternating or symmetric groups acting on the k-element subsets, well, of the vertex set or of the set on which we operate. The primitive subgroups of the symmetric group have quasi-polynomial size. So there's only one family of primitive subgroups, essentially, that is larger than quasi-polynomial, so would cause a real problem in the previous algorithm. But that family is relatively simple. Still, it doesn't help us all that much, knowing that the family is relatively simple. So that's really where Bavai came up with something reasonable. So he refines this divide and conquer strategy. He both has substantial new combinatorial ideas and group theoretic ideas. So basically, we do a refinement. We either find an invariant subset, and that means some progress, or so that's like an orbit, except that Babai works in a different domain, or find an invariant equivalence relation like a block system. Or the third case is identify a simple structure of the problems, something related to these Johnson graphs. Okay, so the first two cases mean progress in the overall recursive algorithm, just like Lux's algorithm did. And the third, well, we have to deal with it. And there, Babai uses a quite sophisticated symmetry breaking to deal with this case. And so he finds a way of dealing with this and with these Johnson groups and still make progress in this overall recursive algorithm. Now, for the smaller primitive groups of quasi-polynomial size, he still uses this brute force idea that Lux already used. Okay, and now let's look at our bounded degree algorithm. But before we do this, I want to highlight one essential property of bounded degree graphs that is used in these algorithms, and that makes the bounded degree case simpler. So we look at a class of groups that is called gamma D. And these are the groups in which every composition factor is isomorphic to a subgroup of the symmetric group of D elements. So in particular, it has bounded size in terms of D. And all the groups that appear in Lux's algorithms are composition factors. So that's okay. Factors, yeah. Okay, so the key observation is if we have a graph of maximum degree D, a connected graph, and we fix one vertex, then the automorphism group, so fixing this vertex, that's this group, is a gamma D group. And why is that? Well, let's look at this graph, degree 3. We fix a vertex, this V. Okay, now by fixing the vertex, as I said, we fix the 3 neighbors of this vertex. Okay, so any automorphism of the graph that fixes V also has to fix the 3 neighbors. So essentially, we only have an S3 operating on these neighbors at most. Now, for each of the neighbors, again, we have actually only 2 new neighbors, and we have an S2 operating on these. And so we have this hierarchical structure of subgroups, and that means the composition factors are only these small permutation groups that permute the children of a node. That's the basic reason why we can reduce basically isomorphism of connected graph to this isomorphism or automorphism problems, where we only look at automorphisms that are in a gamma D group, and that makes the problem much simpler. So to test graph isomorphism for graphs of maximum degree D, we can start this divide and conquer algorithm from a gamma D group that we know is a supergroup of the automorphism group. And that makes the problem easier. And essentially for gamma D groups, because the primitive groups that appear in Lux's algorithm are small, we get a running time of n to the f of d. And then we can reduce the f of d. And actually, what we did then is reduce it a lot to something polylogarithmic. And let me explain how we're doing this. Basically, the first step is we look at the structure of these gamma D groups. So that's purely group theoretic, and then essentially pulling together a lot of results. We have a structure theorem telling us we can decompose the groups into groups of small size, and that's for us size n to the polylog of d, or alternating groups, which are at most ADs, okay? And then we have to deal with these alternating groups, and yeah, that's what we do. And then the second step is a new trick we introduce, and that's maybe the key innovation in our algorithm compared to what Babai did. Well, given some representation of our graph in a gamma D group, what we do is we construct a slightly larger representation and a tree that is somehow associated with this, a tree sitting on top of the representation. And that tree reflects the structure of the group. So the nodes of the tree are in some sense the composition factors of the group. And we can do this in a canonical way. And then we can do, we can basically use Babai's group theoretic ideas. We don't need the combinatorial ideas. And we use them in particular for the nodes of the tree corresponding to these alternating groups in the structure theorem. There we use Babai's ideas, and then we get this n to the polylog d. Okay, so much for this. And now we want to move on to the minors, and I'll be quick, so don't worry too much, but I quickly want to go over this. Now, when we want to look at graphs with excluded minors, we want to look into structural graph theory. Although in the end, the structure theory we come up with is somewhat different from the Robertson-Simons decompositions or structure theory for graphs with excluded minors, because we're mainly after understanding the automorphism groups. Okay, that's our criterion for simplicity. Okay, so the first result concerns tree width. So if we have a graph of tree width k, then we can define an isomorphism invariant tree decomposition. The adhesion, that's the intersection between the bags, is bounded by the tree width k. And for each bag of the tree decomposition, we can impose some invariant structure on the bag, and that's a bounded degree graph. And once we have this in an invariant way, we can use the bounded degree isomorphism test. Okay? And we can compute this decomposition in polynomial time. And now for the bags of the decomposition, we know what to do, but we have to put this together. That turns out to be quite difficult. This immediately gives a fixed parameter tractable algorithm, but not the n to the polylog k. But Daniel Wiebken came up with a strategy of doing this recursively. And it's quite complicated, but I don't want to get into this now. So that's the first step. We know how to deal with structural decompositions. And now we come to a second idea. And that goes as follows. So first of all, I already talked about individualizing vertices in a colored graph. And that just means assigning a new color to these vertices. Okay, and the other vertices keep their color. And now we look at the following algorithm. It goes as follows. We start with a colored graph. We have some parameter, an integer t. Then we apply color refinement, a one-dimensional Weisfeiler-Lehmann, to the current coloring. We individualize all vertices in a small color class. And that's what is new here. If we have small color classes, we can just get rid of them. We can give every vertex an individual color. And then we repeat. We do color refinement again. Some color classes may get smaller, and so on. And we do this until the coloring no longer changes. Okay? And we say a vertex is infected, t infected for this parameter t, if its color class in the final coloring has size 1. And the point is, if we can infect all vertices, we win, we're done. Okay, but let me show you how this works with 2 examples. So here we just have a path, and let's say t is 2, okay? So if a color class has size at most 2, we can split it. Okay, so here we do the refinement. These are the color classes. Now all color classes happen to have size 2. We can split them. We're done. All right. So all vertices are infected after the first round. Let's look at this one. We do color refinement. We get this coloring. Now, the top color classes, they all have size 2. So we can split them. Okay, so now these 3 have new colors, but then their children get new colors. Okay, and now all the children are in color classes of size 2. So we can individualize again, and we're done. Okay, so that's how this algorithm works. Still quite simple. And we call a graph T infected if all its vertices get infected. And for example, if we individualize one vertex, then this argument by the number of children in a breadth first search tree that I gave before shows that a graph of maximum degree at most T plus 1 gets T infected after once we have individualized a single vertex. Okay, and what Daniel Nguyen showed is essentially that we can generalize this algorithm we had before to T-infected graphs to decide isomorphism in time and to the polylog of T. Okay, and the crucial technical thing he shows is that when we spread this infection, we can impose a structure of bounded degree on the graph. So we start with a small set, say, or a bounded degree structure, and then we infect new vertices, and then we can derive a structure, a bounded degree structure on these new vertices, and we can go on like this. Okay. Now, finally, how do we get to the excluded minors from there? Remember, Hartwiger number is the maximum H that KH, such that KH is a minor of a graph. We want to solve graph isomorphism in time and to the polylog of H of the Hartwiger number. Okay, and we start with a structural, or the core is a structural decomposition theorem, and we don't start with this, we want to get there. So let's say we have a graph of Hartwiger number at most H, then we can find an isomorphism invariant tree decomposition. The adhesion is bounded by H, our parameter, and on each back we can find again an isomorphism invariant structure of degree polynomial in H. So very similar to the bounded tree width case. Now the backs don't have to be small. We can just define in an isomorphism invariant way the structure on the backs, and that's good enough. And then we can use Daniel Wiepking's techniques of doing dynamic programming on these trees with the groups to get our polynomial time isomorphism test. And how do we get the decomposition? Basic.
Okay, I'm sorry. Are you nearly done? Or?
I'm nearly done. 3 more slides, I think. I'm sorry.
That's fine. Thanks.
So basically, in these graphs of bounded Hartwiger number, what we show is that the spreading can only stop at small separators. Okay, that's one thing. That gives us the decomposition. We basically spread this infection in one back, and when it stops, we know we have small separators and we go to new parts of the tree. That's one lemma we prove. And the second lemma we prove is that we can construct an invariant small set where we can get started with the whole thing. Because, for example, if we have a cycle, we need to get started somewhere, but we can always find a small set where we can get started. Okay? And then we can transport using Daniel Nguyen's stuff, is we can define on these backs a small degree structure. And there we can use the bounded degree result. And that's all I want to say about this. And my concluding remarks are very short. So the open problem is still, is graph isomorphism solvable in polynomial time? And that's it. Thank you.
Right. Let's unmute ourselves and thank Martin